Hello, my name is Christoffer and you're listening to the Func Prog Podcast. With me today I have Sergei Winitzki. Sergei is a functional programmer who has a background in theoretical physics. He's also passionate about declarative programming and type theory and is currently working on a book called The Science of Functional Programming. So without further ado, here's Sergei.
Thank you for inviting me.
Yes, and thank you so much for coming on the podcast, Sergei. Before I started recording, I think we actually had a pretty interesting discussion that I sort of want to dig into more here. You were talking about like what do you consider to be functional programming? Like you had a list of features in mind that you thought were important.
Right. This is important because in different sources that you can find on the web, people talk about functional programming, and there are lots of books about functional programming by now, and they maybe mean slightly different things, but they have a very common core, and this core is the features that programmers can learn pretty easily and already get benefits in their day-to-day work if they start using those features. So these features, I would say there are four features. First feature is type constructors. So you have type parameters, and you can have classes or objects or functions that have type parameters. So this is a very powerful feature because type parameters can be any type. There are no restrictions on what the type parameter could be. It could be itself a type constructor with further type parameters, blah, 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 blah.
So just to get clarified, so this is what you sometimes would refer to as generics, right?
Generics, correct.
Or parametric polymorphism.
Parametric polymorphism, generics, and types that the compiler checks that you are using correctly with parameters. And that is a very powerful feature that you can start using in many different ways. You can start slow, just making generic functions and applying them, and from there's a deep rabbit hole that goes into functional programming. The second feature is union types or variant types in some languages are called, or what I call them disjunctive types or sum types. So those types are like enum types, except they have extra data. So in Scala there are case classes. They're called case classes. In Haskell they're called algebraic data types. In other languages they're called different ways. In OCaml they're called variant types. So for example, you have a type where you have two variants or two different cases. And in one case, it's an integer, and in another case, it's a string. So it's a type that is guaranteed to be either an integer or a string, and not both. So this kind of type is a very powerful feature that allows you to avoid corner cases, make sure that you never forget any special cases. You can have domain modeling much better with these kind of types. A lot of people talk about this in tutorials, so this is certainly something that you can do. You can do pattern matching on these types, and that's also a powerful idiom. It's interesting to note that most ordinary object-oriented or imperative programming languages do not have those types.
No.
C, C++, Java, Python, they do not have those types. You cannot declare or use pattern matching with those types. And so this is a feature that all functional programming languages have. And the third feature is functions as values. So functions without names. They're called anonymous functions, lambdas, in different ways. But essentially they're functions that you can write without declaring a name for them. You can write them as part of an expression. And you can use them as part of an expression. So this enables a lot of short code that's very powerful. And this is especially for people who know Spark or streaming frameworks like Func and others. That's what's used a lot. These functions that are inside other functions that are inside other functions. So this is a very important feature that enables very short, very powerful code. Not so difficult to learn to use that. Even JavaScript has that. And right. So JavaScript is a functional language, kind of, except it doesn't have types and it doesn't check types. So that's and the final feature that I would consider important for functional programming is syntax for monads. Now this is This is a kind of harder to sell, certainly, because now again the monad. Nobody wants to hear about the monad, right?
No, we got to the M word part of the podcast.
Well, but that is in some languages like Haskell, Scala. I believe in F# as well. There are function expressions. They're called, or some computation expression. That's right. In Python, there are 4 comprehensions, which is similar in spirit to that syntax, but harder to use in Python. In other languages, it's made easier to use, but it's essentially the same idea. The idea is that you write code that looks like imperative sequence of operations, but actually there are data structures behind this. There are very general kind of operations that you can do. You can do sequencing of concurrent operations. You can do sequencing of loops, nested loops, or you can do other things. So this kind of feature makes programming with these idioms much easier. So there are, in some languages, async await constructions, where you write async and then await and then async and await. This is similar, except that so this is a syntax that makes programming with concurrent operations easier. It's the code becomes shorter, easier to read. That's a syntax feature. So this syntax feature is very, very helpful. Async await is limited to just concurrent operations. Imagine the same feature generalized to arbitrary data structures that have similar properties. And that is what Haskell has in the do notation, Scala has in the for yield notation, F# has in its computation expressions, and OCaml doesn't have. So that's a kind of omission. But this feature is very, very, very useful.
Yeah.
So I would say these are the features that programmers use the most.
And so basically you're saying also that like if you want to sell functional programming, you sort of lean on these features and sort of pitch them to like the people who aren't programming functionally yet, and try to explain to them how this makes their code better, right?
Yes. These features are not particularly theoretical in the sense that you don't need to learn theory or math or anything to use those features. You need to learn the syntax in your programming language and the idiom. When do you use this feature, right? And what does it do? And how do you debug code having this feature? And that's it. And once you master this, you already get all the benefits. Most of the benefits of functional programming you already get. So it's I would say that's why these features are having been adopted by several languages by now. Even C++ has some of these features now. Java is adopting some of these features now.
Yeah.
So
yeah, you can sort of see, I think, if I'm not mistaken, like enums, or rather pattern matching, I don't really remember exactly how they fit together, but that's coming to C# now. And I mean, both Swift and Kotlin sort of they also have their own variants of like some types. in Swift you have they have like a souped up version of enums. I guess in Kotlin you have sealed classes.
It's the same thing. It's the union types, disjunctive types, as I prefer to call them, because it's more precise, because it's a disjunction, either this or that, but not both.
Exactly.
But so yeah, a lot of languages are adopting these features because they showed their usefulness.
I think it's interesting that you mentioned OOP, because if you think about it, this is sort of like the same way OOP has multiple dispatch, right? Like when you can say that, for example, if you, let's say I want to model like a traffic light, for example, I can say that, okay, a traffic light, it's either red or it's yellow or it's green, for example. And then if I were to model that in like object-oriented programming, I might, or a better example might be like, let's say you want to model different kinds of like street signs. So one kind of street sign would be like a speed limit, for example.
Yes.
And the speed limit has an associated integer that says like, okay, a positive integer that says like, negative would be very interesting.
Right.
Yeah, you have some natural number that says like how fast can you go here. If it's a traffic light, it has a it has the current color that tells you if you can stop or if you can go, or if you need to stop, for example. And like I guess in OOP you can also model this, but then you have to put all the behavior in the class.
In the class, right. It's not always convenient to do that.
No,
it's not always convenient to put that into the class now.
Yeah, because the limitation is like, let's say I want to program, I don't know, a self-driving car or something, and then it needs to react to these different lights, but it might also need to display them, like maybe if it is approaching a speed limit sign, it should pop up on the heads-up display or something in the car and like show. And like it could also affect the behavior of the module that controls how the car is driving, etc. If you use like discriminated or like union types or sum types, you just declare the type, and then like different parts of the program can react to that. But in an object-oriented program, you have to put all the different behaviors in the class.
Right. Yes.
So
right.
Yeah.
So there's actually in Scala, the disjoint unions are implemented in an object-oriented way, plus the pattern matching syntax, and so objects do approach this in some way, but it's not always convenient. And so the first class support for syntax, making it easy to declare such types, because you can do this in object-oriented way, but it's hard, and the code becomes harder to maintain. I'd like to touch upon an interesting concept that I just recently saw, which is called the Turing tar pit for programming languages.
Yeah.
Right. You've heard about this, right?
Yes. But please elaborate for the listener.
Just very quickly. It's a programming language that is Turing complete. So it can program whatever you want. You can solve your problems with it, but it's not necessarily convenient to do so, because the programming language has certain features that make it harder, or it lacks certain features that would have made it easier. Nevertheless, you have already done a lot of work with this language, and you have a lot of code written in it, which is hard to maintain. But you're stuck in there because you have solved your problems with this language. So it does give you value, and yet you could have done it better in a different language, but you're already stuck in the pit. And so because the language was powerful enough to solve your problem, you don't think about, how do I do it better? Object-oriented programming is an example. So you can solve all these problems with object-oriented programming. You can do a lot of indirection and design patterns and all that in order to improve maintainability of such a program. And the result will be, the millions of lines of code that people have. Instead of thinking in a different way. And declarative programming is another approach that tries to make it better. But if you have already invested a lot of effort, you have a huge ecosystem with object-oriented code all over, imperative code all over. It's very hard to get away from it. You mentioned F#. I wanted to touch upon something we have discussed, which is that F# was designed to be completely compatible with .NET and C#, so that people can start using the features of F#, which are the features I just listed, essentially, without having to stop using all the other code that they already have, all the .NET ecosystem and C# code that they have. So people can slowly ramp up on functional programming features. The same thing, exactly the same thing happened with Scala and JVM. Scala was designed to be 100% compatible with Java and JVM. And Swift and Objective-C. Swift was designed as a functional language, 100% compatible with the entire Objective-C ecosystem at Apple. These languages are functional languages, Scala, F# and Swift, that are very popular comparative to other functional programming languages in the industry because of this gentle ramp up. And the features that people can use are not mandatory, they're optional. So you can still use all the object-oriented features that you are familiar with if you're an object-oriented programmer, and slowly start using functional programming.
Yeah, I guess there's also like a much lower ecosystem risk as well, because I mean, you mentioned something in the beginning or before we started recording that, like, I mean, OCaml and Haskell are two examples of languages that sort of, they stand completely on their own. They're not based on an existing ecosystem, and you have seen, like, you can see that the adoption of those is not as they're not as popular as the other ones. But I mean, if you think about it, like how to sell this to like business stakeholders, for example, if you're telling them like, okay, we can try Scala, and if that doesn't work out, like, we can always fall back to Java and do what everyone else is doing.
Right, because the Scala code will be compatible with Java code, and you can always have a Java library instead of a Scala library if that works. One example from my experience is there was a task that required reading Excel files and extracting data from them. Now, Excel files are a complicated format, and you cannot just read them on your own. You need a library to read Excel files.
It's the XX, what's it called, like the XSLX or whatever?
Yeah, XSLX, right. So this format is quite difficult to implement on your own. So you don't want to implement it on your own. You want to use a library. Now, and then the first question is, okay, do we have a library in the ecosystem that already works and reads Excel files? And in that example, that was some years ago, initially was a Python script that did this, and there was a Python library that had a bug. It was reading Excel files incorrectly in some cases, and some data was not read in.
Okay. So like missing data.
Right. And there's not much you can do. So, people say Python has everything. Python has such a huge ecosystem, but sometimes it doesn't have what you need. So the Java ecosystem had that library in the Apache whatever, and it was working very well. It was this problem never existed. All the Excel files were read correctly. So from Scala, I could use that library. It was one line to read an Excel file. Just like in Python, except it didn't work. Now, if you did this in Haskell or in OCaml, then maybe you would find somebody's hobby project reading Excel files, and maybe that library would have worked for you, maybe not. You don't know that. So it's a risk. It's a risk. Printing PDF files. You want to print a PDF file. It's a huge difficulty to do that. It's a very complicated format. Do you have a library for this? Can we prepare for our customers a PDF report for downloading, for example? Can you do that on your ecosystem? Java, done.
No problem.
If you were using C++, it would be no problem. OCaml and Haskell.
Yeah, see you in 12 months.
Well, see you while I generate bindings for the C++ library that we have, but it's not obvious to generate those bindings, and it will take time, and maybe it won't work, and whatever. So that's these are examples of this risk. So you want to have, there are trivial problems, what you think are trivial problems. I want a PDF report, but actually, so that's also my understanding of why these languages have significant adoption, F#, Scala, and Swift, and yet they're functional languages. So functional languages have these features, but actually some of them have more features. And then there's this rabbit hole that people like to go into. They say, oh, we want to use more features. We want to have more functional programming. Or we want to have, code that checks more at compile time. That, let's say, you have in your program, you have miles and kilometers and pounds and kilograms, and you don't want to mix them, right? You don't want to add pounds to kilometers by mistake. Yeah, it's total nonsense. And so, how can you make types that prevent your program from doing this at compile time, right? So, and that can be done. But this is a kind of a deeper idiom in the rabbit hole. So you go deeper and deeper and deeper. Eventually, you can go as deep as you want. But the question is how do you sell, right? So your question is how do you demonstrate utility while not saying the M word too loudly.
Exactly. Like if you start throwing around words like monads and category theory, like people, they don't even realize what it's supposed to be good for. But if you tell them things that they can relate to, like, what if it was easy to, like, I've noticed when I try to pitch things to like C# developers, they often react they're often pleasantly surprised by, for example, how easy it is to serialize and deserialize things in functional languages, because data and behavior are separate. It's never trivial to serialize an object, for example. But usually, like when you have a record, as long as you can map it to some kind of JSON representation, just find an appropriate representation for all the labels in the record, and you're done basically. But this, if I were to rank, like, okay, what are the cool features of functional programming? I'm not sure I would rank that thing very high. But since it's, I guess what I'm trying to say is that it's always hard to sell people to solutions to problems they don't even know that they have. Like it's much easier to sell them solutions to problems that they are acutely aware that they have. Like they're sick of having to write like these tons and tons of DTO classes just so that they can move data in and out of the system. If you show them, with functional programming, it's easy. You can just do this. Then they're like, okay.
Yeah. I have another example of this. One of my previous jobs was at a startup where engineers deeply familiar with functional programming designed the core code of the server, and then new programmers, new developers came on who didn't know anything about, it was all in Scala, but they learned the syntax, but they didn't really know what a monad is. And they had to learn the syntax for writing new endpoints for the backend server. And this was weird, but okay. So they learned this strange 4 yield with back arrows and all that. Okay, and you can't debug this because the back arrows don't work in the same way. And okay, but they learned how to do it. And I was one of those developers just beginning to learn Scala. And the result was that the code worked the first time you wrote it. So until it compiled, it took some time. But once it compiled, this monad, I later learned what it was. So I was learning functional programming at this time, very focused on that, but took some time. Once I understood what they were doing, I understand now they made a big monad that guaranteed that you could only write code in one way. Otherwise, it doesn't type check. You have to handle all the errors. You have to close the database transaction. So all of that was automatic. So you could not possibly forget to close the database transaction. You could not possibly forget to handle errors or return incorrect status if you have an error. That was not possible. You did not have an opportunity to write such code. You only could write correct code in this monad. And once you learn how that works, then you could very quickly, very quickly, in a couple of hours or in a day or so, make new endpoint, and it worked the first time. So this kind of productivity, this certainly is one example, but this is an example of how this syntax that I mentioned, the monad syntax that many functional programming languages have, how the syntax, at first it is unfamiliar, but actually it helps write code quicker and with fewer errors. And of course, monad. Well, monad is a very important design pattern in functional programming. You don't have to say this word necessarily, but in my view, it's not so important to say that this is a monad or this is, computation expression or whatever. You have to learn what it is. You have to learn how to use it, and once you learn it, you're done.
Yeah, but I like that phrasing, like calling it a design pattern, because that's really what it is.
Yes.
Although it has a solid mathematical foundation behind it, but for day-to-day programming.
Let me just catch you by your words.
Yeah.
So you somehow think that design patterns do not have the right to have a mathematical foundation, right? You're excusing the monad design pattern for being mathematically well-founded, right? And to have mathematical background, because usually they don't, right?
Yeah.
Because usually design patterns are just what?
Yeah, it's just basically repeated, a recurring pattern of code, or like a ready-made solution to a specific problem.
That's right. Yeah. So it's somebody's experience, and you're just repeating their experience because it works. And monad is not like this.
It's very nice to have these kind of guarantees, because it sort of allows you to reason about the program in a more solid, well-founded way. If you know that something is a monad, you know that there are specific guarantees of things that it can and cannot do, and ways you can compose them, etc. I think this is one of those things. This was a real eye-opener for me. For example, when I started doing this more typed functional programming, all of a sudden it was one day I sort of realized I don't even need to know what all this code does. I just need to look at the types.
Right.
It's sort of, just plugging in. If you plug in a computer into an outlet, you don't need to know what kind of power the computer expects to have. The charging, the charger takes care of all of that for you. It feels like imperative or procedural programming. It's sort of as if you would have to sort of have some like different knobs you would need to adjust, like on the charger. So like to I don't know, get the right voltage into your computer. Like with functional program, it's like, okay, if it connects in this end and if it connects in that end, I know that it works. Like I don't need to think about like, okay, does this thing change some global state somewhere? Like, does it throw exceptions, etc., etc.? No, I can just like, take these pieces. If they fit together, I know they work together. So I guess that's sort of what you were going for with the what do you call it, like the mathematical foundation.
So I would like to comment about how programmers come to grips to all this. So first they learn the mechanics, how they write the monad code. They don't know it's a monad. They don't know the laws of the monad. But they know they have to write this, then they have to write this, and then if they don't write it, it doesn't compile. So the second step is to understand, well, actually, it's as if first I do this, then I do that, then I do that. And a little bit like imperative sequence. A little bit, not quite, but similar. And then they say, oh, maybe I can switch some order of things in there. Or maybe I can refactor a little bit in there. And then they learn that they can refactor, it still works.
Yeah.
But that's actually the monad laws. And so they don't know that, but okay, well, it's working. And that's it. They don't actually need, the programmers don't actually need to study the formal mathematics behind it. If you want to study it, you can, but you don't have to. It's more like an engineer who learns, okay, there is some science, some, let's say, electrical engineer. There is some science of electrodynamics behind this, but I just know that, this resistor needs to be here, and this voltage needs to be like this, and then I do that, and then I do that. And it works. I can see that it works. I put it in, I plug it in, it works.
You don't need to know the theory in order to use it. You don't
need to know all the derivations, all the proofs. You don't need to study that in order to use it. You need to know something about it, but not necessarily all this mathematics. So actually, let me comment that often in discussions on functional programming, people talk about category theory somehow being important, and or formal logic being important, or other things. So, in fact, it's not clear what is the theory that programmers need to learn. It's far from clear. Category theory books are far too abstract. Formal proof and formal logic books are far away from any practical application that programmers have. It's not obvious what exactly that science is that programmers need to learn, actually need to learn in order to be productive, in order to write correct code. Right? So depending on their code, so for example, there are things like monad transformers. It's an advanced design pattern, which is hard to use because you need to know a lot about them, and it's not obvious. Well, it's not often used. So most of the time you're fine without it. There are other such things like free monad and such other patterns, which are not easy to use, not easy to understand, and not often used. So what I'm saying is that programmers have to begin with specific features and specific programming language where they slowly learn how to get benefits out of these features. And some people will be interested in mathematics, they will learn it, others won't.
So basically what you're saying is that like you sort of start with a problem, for example, like in my other programming languages, my program type checks, or maybe I don't have any types. Then when I run the program, it doesn't work. So the solution to that is to have like stronger type systems with some types, etc. So you can make like illegal states unrepresentable, like Winitzki said.
That's a very good idea. Yeah.
And then you sort of start with you start with the problem, you move on to the solution, which is to sort of like use these powerful type systems, and then you can learn, like if you want to, you can learn the theory, like, oh, by the way, this is called a monad, and like a monad is supposed to uphold this contract, or like obey the monad laws or whatever. And then you can learn about category theory and stuff if you want. And I feel like sort of the issue with a lot of, like, for example, the classic, monad tutorial that's like that trips so many people up, is that a lot of them are written the other way around. Like you start with the theory. Like you start talking about, okay, what is a monad, etc., what are its properties, and then you move on to sort of like the implementation, or like what is it, and then finally you end with sort of the problem, like, okay, so this is how you can use it, like, so. But you're basically saying that it's much better to do it the other way around, like start with the problem, move on to practice, and then you can
start with specific benefits that you get from this feature. So there's a feature that I don't know, that C++ doesn't have, right? So how do I get benefit from that? C++ has many other things, but not this. So even I would say category theory is not really what programmers need, and there are very few actual results from category theory that you need to understand. Very, very few. There are maybe one or two situations where it becomes helpful to learn a little bit about category theory as such, to understand, there are categories. What is a general idea of a category? There are very few situations when that is useful for a programmer. The programmer needs to answer questions about code. What is the correct code? What are the properties of the code that I have? To answer those questions, I would say category theory is not particularly helpful. Programmer does need to learn certain things, but that's not category theory. And that's actually, if I may make a pitch for my book. So I've been writing a book about functional programming theory, exactly trying to answer this question. What is the theoretical material that the programmer needs? What does the programmer need to understand? And my approach in writing this book, so this took I'm still writing it. It's kind of, last chapter is not yet done, but it's kind of almost done. My approach is to begin with code and with questions that the programmer might ask about code. So, for example, what is the type of this expression? Or how do I compose these two types or functions or something like this?
Okay.
Right? What properties does this function have? Does it, can I write some equation that it satisfies or something like this? Can I prove that this function have that property, or can I prove some property about types, that this type is equivalent to that type? Then I can simplify my code. I don't need to use a complicated type if I can use a simple type, if they're equivalent, right? And so on. So these questions are kind of starting from code, going a little into theory, but always starting from code, never starting from theory. Not saying, I have just learned about this cool thing in category theory. How could I use it? What kind of code could I write? Maybe that's pretending that I'm using that theory. That is not the approach that I wanted to take. So I wanted to, for example, there are functors, monads, applicatives, and where do they come from? Why am I supposed to be interested about them, right, in learning about them? Is there code that I can write if I learn those things? Is there some new code that is easier, better, faster, whatever, I don't know, that I couldn't write before until I learned those things?
I see.
If so, then those things are really design patterns for my code, right? If not, then they are just theoretical things that some people like to brag about. And I'm not so much interested in that kind of thing. You know, I have my previous career as a research physicist. I did a lot of theoretical work that has no application. I can easily see when something has no application. So,
yes, you learn to spot those.
Right, and I can see. So I can go through. So in my book, I go through specific code patterns that people know are useful. For instance, the MapReduce style of programming. What that was, or what the Spark is based on. And Spark is essentially MapReduce on steroids. It's a much more general and powerful framework that is automatically parallelizable. What are the building blocks of that? What are the properties of those functions? Map, filter, reduce, flat map in Scala. In Haskell, this is called bind. I don't know what it is called in F# really, but
usually bind as well.
Bind. So, what are the properties of these functions? Why are these functions like that? Can we find more such things? Maybe we're missing something here. What are the other things that, for example, filter? What are the properties of filter? Traverse. There's another thing called traverse. So what are the properties of that? What are other such things? So what other data structures can we use with this? Right. So we can use, for example, Spark has this RDD data structure, which is a automatically parallelizable array. It's a huge array where you write the code as if this entire array is already here, but actually it is not. It is parallelized across different servers and so on. What other data structures could have the same properties, the same functions, map, filter, bind, reduce, and so on? Maybe
so
not
like a
only
tree
arrays.
or a set or a heap.
Exactly. Or maybe some other data structures, maybe smaller data structures, like even finite, not necessarily this collection of arbitrarily many things, but maybe smaller data structures, your algebraic data type, your sum type with some parameters, maybe it already has these properties. Maybe you can use that also with this. What are all the data structures that could have map, filter, reduce, or maybe some of these but not others, and why not? What is the problem? How do you fix that problem? These are questions that I started to grapple with, and eventually I went through a lot of mathematical derivations that showed me what the laws must be of these functions, whether they satisfy these laws, and what are the proof techniques, the calculation techniques that you need, and what is the notation that is best to use to make those calculations, to write down the proof. So I went through all of this, starting from practical questions and going into the more theoretical direction a little bit, as long as I felt that there was still some connection to practice. And so I have in my book, in some sense, outlined the scope of material that a functional programmer might possibly want to learn.
Okay, so that's sort of like a roadmap, would you say?
Yes,
or
yes. So the roadmap starting from MapReduce and Spark and going a little further, just a little further, like, for example, type classes. What are the properties of type classes? Just to give an example, the product of two functors is always a functor. Product of two monads is always a monad. Product of two monoids is always a monoid. Product of two blah is always a blah. Why is this? Can we perhaps understand that there may be a general property that for some blah, product of two blah is always a blah. So what is that? How can we write that? That is as far as I want to go theoretically. I don't want to go any further than this. So if I can prove this, I'm happy, and I stop. I stop this theoretical investigation. I've proved that these properties hold for all type classes of a certain kind, and I'm happy, and I'm back to work, essentially, back to coding. So now this is just an example of a property that is quite theoretical. It requires some category theory a little bit to prove some concepts from category theory, but it's in my view it is relevant to programming, because then you can build data structures from building blocks, and you can still have properties that you want. So anyway, so this is the kind of book that I have written, where a lot of things are explained that you don't usually get explained. A lot of things are derived and proved that usually are not derived and not proved. In my book, I begin each chapter with practical code, and then I talk about the laws, and then I talk optionally about more theory that, that's not really... So I want to make it clear that there is theory behind all this. It's very different from object-oriented programming, from logic programming, from other kinds of programming. There's theory that helps you write code, that tells you what code to write. It's never the case in all the other paradigms that there is theory that you can first make some derivation, and only then you understand what type you need to put into your code as a data structure type. And like you said, the types say quite a lot about the program already, and that's very important. So if you can reason about types, that guides you directly about how to write your program. This is a unique feature of the functional programming paradigm, that it actually tells you how to write your code in some, not all of it, but in some aspects.
Yeah, it sounds like a great book. What was the title again?
The Science of Functional Programming.
The Science of Functional Programming. I'll make sure to link to it in the show notes.
Yeah, I can.
And
please,
it does sound like a book that's really needed, because I remember this was something I kind of struggled with initially, or like when you start doing these things, it feels like, I mean, you can grasp the basics, kind of like how map works, or how bind works, and you kind of sort of understand what a monad and a functor is, etc. But it feels like what I hear from you is like this book lets the reader sort of take the next steps, like how do I actually use these things, like how can I reason about them.
At least that's the vision of this book. I tried as hard as I could to do that, and I'll be happy if you give me any comments, or anybody else gives me comments, but in any case, thank you.
And you can get like an early version of this book today, right?
Yep. It's almost complete except for one chapter. It's a free book, so you can download from GitHub, or you can, the nice PDF you can get from LeanPub, and but it's a free book. So
okay, hear that, folks? It's for free.
It's for free. It's for free.
And you can give Sergei money as well if you want.
Very little money, so kind of minimum price on GitHub, on LeanPub, and for GitHub you have to click through 3 different links.
Okay. But feel free to give Sergei a lot of money if you feel
No. This is like no. I'd like to say you can't make money on books today. So unless you're writing things like Harry Potter, you can't. So you shouldn't think that your book is for money. The book is for because you want to say something.
Yeah, you have something to say, right? And I noticed that you're not only working on, or you have this book, which is like almost complete, but you're also working on another book, right?
Yes.
Or maybe that's done already.
No, it's not yet done. The other book is about the Dhall language.
The one by Gabriela Gonzalez.
Yeah.
Please tell me more.
Yeah. Well, I first encountered this language a few years ago. It's a language that was positioned to replace templating for JSON and YAML. So this is how they're selling this language, right? So, but actually, if you look at the design of this language, it's a purely functional language, which has all the features that any functional language ever wants. a purely functional language, of course. It's consistent with the restriction that it's a configuration language. So it should not be just arbitrary code execution. It should be safe to execute that code because it's your config file, essentially. So you run a templating script that prepares your config. And that script should not be arbitrary code. It should not go into infinite loops or, allocate infinite memory or something like that.
It's a what you would call like a total functional.
It's a total functional programming language. So it's not Turing complete, but that's actually not a great disadvantage. You can do a lot of things with it if you want to. I'm not sure Gabriela would be happy with all kinds of things that people can do with this language or with my book. I'm not sure she would be happy with my book because my book says Dhall is essentially system F omega, and system F omega is the same as Haskell. There's no difference, except for one feature. Haskell has recursion and Dhall does not. And for me, this was a very interesting experience. It was the first time that I saw how to implement a programming language, and it's documented. So Gabriela documented all of that for anyone who is interested, and it's relatively straightforward to implement. Of course, my implementation is slow, it's inefficient, it's not production ready in any way. But my goal was learning. So what I learned is that you can.
You implemented this in Scala, right?
In Scala, that's right. Yes.
And where you can read how to implement Dhall. Is there like this documentation you were talking about? Is that available on the Dhall website?
Yes. Yes. There's a official website. It's a GitHub. There is a website with documentation, and there is a GitHub with technical documentation. So it's not user-level documentation, it's documentation for implementers, which says, precisely specifies the language. So it's a formal specification of the language, which is unambiguous. And so you can implement that and run all the standard tests, and they should pass. Now, they didn't. I reported a few issues, and they were fixed, so by now it should be all fixed. So this language teaches you what it means to do functional programming. It's a very bare bones language. It has just a few features for convenience, like records and union types, and that's about it. These features don't add to the expressive power of System F, because System F omega is powerful enough to imitate those features. If you didn't have records, it could imitate records or union types using its own types. The types are so powerful that you could do really mind-boggling things with it. But the important experience for me was, okay, so here's this language which has comparatively few features. I was able to implement it in a few months. Of weekend and evening work, and it works. It just opens your eyes to what functional programming means. Everything is so clear. Haskell, Scala, and other languages, they put more emphasis on usability. So they make syntax a little easier to use. Also, how the compiler should work, and type checking, and IDEs, and everything. This language doesn't do that, so it just is a bare bones. So like every function has one argument, period. And then if you want more arguments, you can curry. No
exactly.
problem.
So it's instead of like every function, if you have more than one argument, you get another function back.
Yes, you get another function back. And you write all those types explicitly. There's never any implicit type anywhere that is magically hidden. Everything is in your face. So if you want to do something complicated, that complication will be in your face. You will see, okay, here I'm actually doing something pretty complicated with a lot of parameters, a lot of types that are kind of difficult and complicated, and I have to make sure that everything fits. In language like Haskell, it's not always obvious that you're doing, complicated things, and a compiler gives you an error message that you don't understand because actually you wrote something much more complicated than you thought. In this language, in the Dhall language, nothing like that happens. So it's really, in my view, it's a good vehicle for learning the patterns, the idioms of functional programming. You can implement everything you want: map, reduce, filter, all the collections. You can implement type classes. You can implement free monads. You can implement whatever you want. You can implement all those things, even though it's not Turing complete, which shows me another such thing, eye-opening for me. Turing completeness is not a goal. You don't want it. You don't want it.
I've been starting to think the same thing, actually. Like, which is also a bit strange, because like when I was coming up, when I first learned about functional programming, it was through Paul Graham and his essays on Common Lisp, etc.
Yeah.
And the Lisp folks, they are really into recursion, right?
Right.
I mean, they love their recursion, and then suddenly. I think it was also when I started reading Gabriella's writings, and it's like, suddenly someone comes up and says, no, recursion is bad, actually. And I was like, what?
Yeah, recursion is dangerous. It's like a go-to. It's not as bad as go-to, okay, but if you have go-to, you can do recursion. Like if you imagine a language like BASIC with no recursion and no functions, but with go-to, you can do everything you want. Right? you can do all kinds of recursion just by hand, just by doing go-to to the right places, and so it's actually quite difficult to remove recursion from a language.
Go to the ultimate.
Yes, but Dhall does it in a principled way. You can prove that there is no recursion there, that everything terminates. Also, this makes no difference between lazy and eager evaluation, because everything is terminating, so there is nothing that you need to worry about in that space. It's a big problem in Haskell that sometimes you don't realize that certain things are lazy.
Yeah, so you have like start eating up lots of memory, like for unrelated things.
Well, right. So, but I'm not saying that Dhall is a language that you should use for programming instead of F# and Haskell. No. Dhall is a fantastic language for learning, and I still believe its original mission is correct, to replace all this convoluted and illogical templating languages for JSON and for YAML. They're so difficult to use, these templating languages, that people have to use. And they're not principled, they're not logical, they're difficult, easy to make mistakes in. And so Dhall replaces all of that with principled language that at the same time gives you a typed schema for your data and the data itself, and it verifies that the data fits the schema, and the templating. And you can have functions that refactor repetitive configuration into pieces, and you can have modules where you put things in different files and you import them. And everything is safe, and everything is just great. So I try to use it at work a little bit. So yeah, it's working. It gives me good configurations, YAML that is always correct, and that's fantastic. But for me, you can say it's not Turing complete, doesn't have recursion. How can you even program anything if it doesn't have recursion? Because it doesn't have loops either, right?
Yeah.
It doesn't have while loops, it doesn't have for loops, it doesn't have goto, it doesn't have variables that you can modify. How do you do recursion? How do you
get anything done?
How do you get anything done, exactly. But actually, a couple of months ago, I implemented routines for floating point computations in arbitrary precision. So I computed 100 digits of pi using Dhall. Now, this was a stupid exercise, I would say, for no particular gain, except for understanding, right? So what can you do? Well, you can do those things. You can do, arbitrary precision computations. You can compute pi to any number of digits if you wanted to. Because that computation is guaranteed to terminate, you can always formulate it in a way that does not involve recursion. It involves finite substitutions. So 100, there are many things that you need to be computed, but it's a finite number of them, and you know in advance how many. So instead of a loop, you write a function that is applied to an argument a fixed number of times. So you can do that. And that number of times needs to be fixed in advance. Right? So you can apply it 100 times if you want, but you can compute f of x, f of f of x, f of f of f of x, and so on. You can compute that, but you need to know how many times in advance. So if you know in advance that you only need 100 times, Dhall can do it. So that kind of thing is okay. It's not really recursion, right? It's kind of very limited. And if I think about what kind of logic one needs for general applications, for mobile applications, for web applications, for what kind of logic do you need? Do you really need recursion? Do you really need to compute complicated recursive functions? You need to add an item to a list or delete an item from a list. Okay, well, that kind of computation is not recursive.
Yes.
List is a recursive structure, but you know in advance how big it is. It's on your screen. Or you fetch your list from a database, you know in advance how big it is. You're fetching the next 100 elements and no more, right? So you know.
Exactly.
So do you really need a language that allows you to have unrestricted while loops and recursion and so on and go to and that? Probably not. Not in most cases.
Yeah, I think that thing is really interesting. Like, how can you, it feels like most languages today, they focus more on more features, more power. But what if you did it the other way around? Like less power, less features. Yes. Then all of a sudden you can do completely new things with these languages. Like you said, generate configs. I mean, it's kind of dangerous to run Python, arbitrary Python code in your CI system, for example. But if you're on Dhall, you know that, it's going to terminate. I don't need to worry about having to go in and kill a process on the machine because it's eating up all the CPU.
Right. Well, you cannot do a fork bomb in Dhall.
No.
And you cannot, as a pitch for Dhall, I would say, this is a language that is like a programming language. It has a module system, it has types, it has values, you can compute various things, and yet completely safe and guaranteed to terminate. Now, there are certainly reasons not to use Dhall, and there are competitors to Dhall in that space, certainly. There are at least 5 or 6 similar languages that position themselves as configuration programmable languages, where you generate JSON or YAML from a script, and the script is limited. So it's not just arbitrary Python code that you import from the web in order to generate your config, right? Right? No, so this is guaranteed to not do anything bad, and yet many of these languages are Turing complete because they just, why not? Some of these languages are even object oriented. So you have to write classes and methods in there and objects and think about late binding and overriding and all that stuff, which in my view makes programming just complicated. And there are languages like Nickel that is trying to do similar things to Dhall, but it has gradual typing, which in my view is a mistake. Typing cannot be gradual because people will use no typing. People will just go all the way to no typing. Look at Python code.
It's I never really understood the rationale for. I mean, I can see it, why you would do it when you're sort of trying to add a post facto type system to a programming language. Then it makes sense because it actually makes migration viable. But I never really got the reason why you would start from gradual typing, because like you said, people will use the any type or whatever, and then you have to deal with that.
Yes, because they would not think that there is a different way. They would think gradual typing was sold to them as a gradual ramp up to typing. Okay, well, we are used to no typing. Now we're going to sometimes use typing. That's their idea, right? And then they look at some JSON blob and they think, okay, well, this, I don't know how to type it really. Sometimes, like last week I was looking at something called the Amazon Step Functions language. I don't know if you've ever looked at that.
It sounds a bit scary.
Yeah, right. Completely JSON-based language that describes workflows.
Okay.
Right? So on AWS, right? So you can upload the JSON and then would run your workflow. So, but how is this JSON to be written, right? So it's a programming language right now in the syntax of JSON. Okay, well, here must be a string which must be equal to this other string, or it must be equal to one of those other strings. And if this is here, then this cannot be there. And if this dictionary is here, then you must also have this other thing over there. And end.
Yeah, I recognize that from, like, I had in a previous life, I wrote a lot of like CloudFormation templates. Sounds very similar.
Right. So a programmer would not necessarily think of, okay, well, this mess needs to be strongly typed, first of all. Right? And if it's not strongly typed, like I'm comfortable, but they are perfectly comfortable. Right? So they would say, okay, this is too complicated to have a single type, so let's call it any. Next JSON blob, okay, it's again too complicated. So that's what will happen. Actually, it's not easy. Some of this requires dependent types because the value in one place determines the type in another place. So sometimes you can model this using algebraic data types, right? But sometimes you can't. It's a really dependent type. So it's a difficult problem for any language except Dhall. Dhall has dependent types. You wouldn't think, but it does.
Yeah, that's something that fascinated me. That's something I just learned only recently, that it actually does have dependent types.
Yeah. And another thing that is interesting about Dhall is that intentionally it forces you into strict typing where you might want to use strings instead, stringly typed, this kind of idea. Because in Dhall, you cannot compare strings for equality.
Oh, yes, that's true.
Right.
But why is that? What's the rationale
Gabriela explained it to me. So,
okay.
So I can say what I understood. The rationale is that users will start using stringly typed data structures
to get away from
string typing. If you allow them to compare strings for equality, they will say a record whose first field is type, and it will be a string, and then they will do comparisons on that string to determine other things. Instead of having a union type, where the type is not a string, is a type, and the compiler can check that the types are right. Instead of that, people will start using stringly typed things, and they will start parsing, and they will start doing all kinds of things which they shouldn't be doing. Instead, they should be doing not parsing, but modeling, domain modeling using data. They should not just say, oh, this is a string, and then I will parse that into JSON. No, they should.
Then you're back to where you started, essentially.
Exactly. So this was the reason why Gabriela resisted any attempt to put string comparisons into the language. And yet you can do kind of string comparisons, but not at runtime. You can do that at compile time only. In other words, if you wanted to say that a certain field in your JSON must be empty, string, you can assert that.
So you can do it like a
compile
value.
time.
Yeah.
Compile time assertion you can do for a literal string. You can say, well, this literal string must be equal to that, or this whatever. You can do assertions, and assertions are at compile time, but you cannot do anything like this at runtime, which could fail. Nothing is ever allowed to fail. So if it compiles, it must work. This is imperative, and that this totally resonates with everything I have learned about functional programming so far. This is the goal. If it compiles, it may not crash.
Yeah. It's like I was actually quite surprised when I started to learn Haskell. Is that like Haskell does have these functions that you call like partial functions. For example, if you try to get at least if you use the standard library, if you try to get the head of a list, Haskell can crash if the list is empty, for example.
Right.
And it can still do like divisions by 0, etc. And in Dhall you can't do any of that because then it wouldn't be total. Then you couldn't be sure that it would terminate.
Yeah. Dhall does not have division because it could fail.
I have to do with multiplication instead.
Well, you can do division. You can do division by hand, but it's not built in. Now, how to build it in correctly? It's a good question, but it must not fail. It may be whatever you want, but it must not fail. So, So that is another thing about Dhall, is that you can abuse it as a system of omega. You can write monads in it, and you can write whatever in it, which probably defeats the purpose of this language according to its designer. But to me, this is a very interesting vehicle for learning. And if you can argue that some features shouldn't be there because it makes users go in the wrong direction, I agree with that. But for example, you can do compile time assertions, and that's a very powerful feature that makes your data structure validated. So you can validate your config before it is generated into JSON or YAML. Very, very powerful feature. It's a big problem, I think, today, that configs are not validated. They're not tested. They're only tested by deploying them. Right? So you deploy your config, or like at work we have Kubernetes, so you write a huge amount of YAML. How do you test it? You deploy, and you go to the cluster, and then you look at what happened there. Something wrong happened, you roll back. So that's how it works. We don't test this YAML in any way. There are no assertions on it. There are no properties that you verify for it. There's no test that you run for it before it is. There are some basic tests, of course, but they're not sufficient. So it's very, like in YAML, if you include an empty line somewhere, it could be completely different than without the empty line in certain cases. So you put that
and you try to type Norway. So you use like the abbreviated no, and then you get a boolean that's false. And it's like
and you will never know. You will never know because false will be converted to a string, and so then your application will have a country called false, and your application will not complain. This is a name. This is a string. And you will never know why your feature doesn't work. Why Norway is buggy, and other countries are not buggy, and so. Enter an empty line in YAML somewhere. In certain cases, in some templating languages, this would completely change the meaning of the template, and you will never know. You will never know. It's not an error. There's no, just part of your YAML will be silently put somewhere else or ignored or whatever. So Dhall makes those things impossible. And you can do assertions, you can do all kinds of interesting things. You can program in this language. And so I'm writing a book about functional programming seen from this lens, from the lens of Dhall, system of omega, total programming, guaranteed termination, all types in your face. So you know if you do something very complicated, then you have to write it out. You have to. There's no shortcuts or implicits or anything. Everything is explicit. So To me,
no
this
type
was
inference.
No type inference at the moment. There might be eventually some, but it's against the design of the language. The language is intentionally designed in this way. You shouldn't be doing complicated things with it. You should be creating your data structures and refactoring them with simple functions. And that's pretty good. And that's not difficult. You shouldn't be doing, free monad transformers in there. And if you are doing them,
although you
can. You can, and you're on your own. So please write all the quantifiers explicitly and everything explicitly and all the type parameters, and you have 2 lines of type annotations before every line of your code.
I think that this is really interesting because it sort of goes back to something that you mentioned before, is that the ergonomics of a programming language matter. Like if it's easy to do lots of like advanced type level juggling, people will tend to do that. But if and same thing with like in like object-oriented languages, you have this term called like primitive obsession, right? When people use, instead of like if I want to represent an email address, people just use a plain string, but the danger there is that like then it can be confused with any string. If you have a function, for example, that accepts like a username, a email address, and a password, and all 3 of them are strings, it's very easy to mix those up. And so the term primitive obsession sort of warns people against this, like, create an email class instead, create a username class or something, so you don't risk mixing this up. But I feel like the problem from the beginning was the fact that it's, object-oriented programming makes it hard to create new types. So people tend to avoid doing that. Just like you said, like people try to get around the strictness requirements in Dhall because they want to write like stringly typed languages. But then, Dhall comes and like sort of like gives you a gentle smack on the fingers and says, like, that's a bad idea. Don't go there. And at the same time, like you said, it also tries to stop users from doing like this advanced type level gymnastics, because you have to like type, you have to write out the types explicitly.
Yes, and well, for me it was a very, very helpful exercise to be able to write those types and to understand what's going on. But also, maybe it's not really so useful. Maybe if your free monad transformer is really so useful for your program, then you can bear all those interminable type annotations. But you must really have a good reason for using it. And in Haskell, it is the other opposite. Everything is so terse, right? All the types are implicit. So you can write things like fmap, and fmap has complicated type signature, but you don't see it in Haskell. So, like you said, you can easily write very complicated types, and you don't necessarily want to write them, but one particular funny thing about Haskell, you can write things like fmap space fmap space fmap space fmap. You can write that any number of times, and it's still well typed, because Haskell can find some very complicated type parameters that it substitutes implicitly into every place, so that all of this still makes sense as an expression. And from a user's point of view, that's just an error. You didn't want to write that, but nobody wants to write that. But from the point of view of Haskell compiler, that's not a problem at all. The type of this can be inferred automatically, and it is inferred automatically, and then it's given to you. And if you didn't know, then it's your fault. And so there's a balance. The programming language must make things easy that it's designed for, and the difficult things should remain difficult, perhaps, because users don't necessarily want to do that, and if they do it by mistake, they should know that they are doing it. So yeah, in my view, but this is just an opinion. So again, this is it's a very difficult question, a question that I was fascinated with for a long time. What is a good programming language, right?
Oh, that's a good question.
Because we seem to come up always with new programming languages all the time. Do we really understand what went wrong with the previous ones? And, why do we need C++ 11, C++ 17, C++ 23, and Java 8 and Java 17 and Java 22 and all that? Is that really correct, the correct way of doing it? And one approach to programming language that I understand is the idea of declarative programming language, right?
Yes.
And domain-specific language and declarative programming language. And this idea still means that you need to create new programming languages, but you need to do it in a specific way. And so I don't know if it's interesting. I can expand on this.
Yeah, sure.
The idea of declarative programming is that you write code that looks like the statement of a problem. When you read that code, it's clear what is the problem is. What is the task that needs to be done? It's clear to people. So people read that code, and it's obvious what it is. There's no question about what needs to be done. Like, imagine a language that says, first, turn on the machine, then press this button, then do something else. It's unambiguous what needs to be done. And at the same time, the computer can compile this description into an executable program, and that program is guaranteed to do exactly that. So examples of declarative language is arithmetic. The sub-languages of arithmetic that today every programming language has. You write A plus B divided by C. You don't think about it twice. You just write it. And it's obvious what needs to be done. A plus B divided by C. First you divide B by C, and then you add A, not the other way around.
Yeah.
Right? You don't have to write tests verifying that indeed that is what happens.
No.
Right?
It's so common that you don't even think about it.
Nowadays, we don't even think about it. It used not to be common, right? It was an invention in the 50s, invention of the Fortran language, which for the first time allowed you to do such a thing. And before that, you had to do a lot of other, low-level stuff. And maybe you needed to write tests to make sure that you have freed the memory from the plus operation or whatever. Now you don't. So this is an example of a very well-fit declarative language where you write just a statement of what needs to be done, and the compiler automatically and correctly always translates that into the executable code that runs correctly. Another example is SQL, the database query language, where I would like to say just the SQL without the stored procedures, without all the pragmas, with none of that stuff, just a bare, simple SQL. Without
Standards.
recursive standard, the early standard, without the recursive queries, without all that stuff. Just you say select users from whatever blah blah blah, where the date is such and the department is such and so on. That's it, and you just write what needs to be selected, and it is selected. It is given to you as a data structure. So that is an example of a declarative approach. It doesn't really matter if it's written in kind of English-like language or not. That's not important. It's important that when you read that code, you know exactly what will be done. Exactly what needs to be done. Not how it will be done necessarily, but what needs to be done.
I guess that's an important distinction as well. Like when it comes to declarative, that the focus is on what, not the how.
Yeah, well, this is what people usually say, but it's not enough to say that, because you need a language that describes your task unambiguously, such that this language is understandable to people. immediately understandable to people. You should not be writing tests for this. You should be just reading it.
It should be obvious.
It should be obvious what it does. So this property of being obvious to people, it's a very difficult property to achieve, actually. And that is the main difficulty. We don't know how to achieve that in a given problem domain. So if I give you, if my problem domain is control programs for microcontrollers that drive robots or whatever, right? I don't necessarily know what that language is. Or if my problem is to write iPhone applications, right, or something, I don't know what that language is where I can unambiguously specify what needs to be done. So that's actually the difficulty. And the whole effort around declarative programming and domain-specific languages is trying to come up with that language and testing it and then failing and then fixing that and then again failing. Because eventually select, it becomes unreadable, right? Eventually a formula that is 5 pages long becomes unreadable. So what do you do then? Well, you need some features that maybe modularize, maybe something else, or type checking, or all that stuff becomes important. But anyway, this is the main approach. The declarative programming, the ideal is that. And how close are we? We're pretty far from it in pretty much most languages. So one good feature of functional programming, Scala, Haskell, F# perhaps as well, I don't know, is that you can create domain-specific languages within your language by
like using the monad notation.
Using computation expression in F#, using do notation in Haskell, or syntax extensions or other things. You can create a small language which is entirely within your language, which kind of looks like the description of the problem, which kind of looks like you are just describing line by line what needs to be done. And then, ideally, if it compiles, it runs correctly.
Yeah, that's the important, an important property to have.
That's the ideal. That's what you're striving for. So this functional languages allow you to do this, I would say, easier than other languages. Because functional languages more strictly check what you write than other languages. And so you can put types, you can make very expressive and complicated types in this DSL so that invalid DSL programs do not compile. Right? So imagine you have, I have this example in my book, you have a DSL that reads files and writes files from the disk. So suppose you read a file. So the operation read has an argument which must be a file, and the result of that may be a string. But when you write when you say read of file, that's wrong, because you're not reading a file. But so how do you make sure that this doesn't compile, right? So you don't want to do this ad hoc. You want to prevent all of these things from compiling. All incorrect usages must be failing to compile. And so functional programming gives you the type system, and gives you the flexibility and power of the type system with type constructors, with all the kinds of things that I talked about, to achieve this. And so you can actually achieve very good DSLs. Scala has a lot of open source projects that introduce DSLs, and maybe a little too much. With all kinds of squiggly symbols that that are difficult to understand and to remember.
It's an entirely new language you have to learn.
Exactly, yeah, and it's when you do it too much. So actually, there's a backlash now against this in the official Scala development. They say avoid that. Use methods that are just words, and don't put squiggly things there. Right, don't, because it's unreadable and it's hard to remember, and so, but this is kind of a trade-off. So then you're like Python. Everything is very verbose. You write all those things, or Java.
first do this, then do that, etc., etc. I guess there's always like a balancing act, right?
Yeah. So this is an open question: how to design a good language. And my answer would be try to design a declarative language for your domain. Another thing that follows from this idea is that it will be different for each domain. So there won't be one language for everything. Each domain will have its own, maybe multiple languages for parts of that domain even. It's impossible to achieve declarative programming across all domains.
Yeah, no, it has to be, like you said, like domain specific. Have you read the also post on the Gabriella's Haskell for All blog about what's it called, like the end of history for programming languages? Have you read that?
No, I don't think I have.
No, but it's
end
very
of history.
It does go. It sort of says pretty much exactly this, like, you know, that she believes that it's going to be like you will see a development where people start developing like their own bespoke languages for like their own specific domains, right? Because you always have and I believe this too. I sort of like, it feels like there's been a pendulum swing, sort of like in the beginning, where in the beginning of computing, where pretty much everyone created their own like bespoke programming languages. We sort of made a shift towards general purpose programming languages, but I think we're sort of running into a wall about what you can accomplish while still like keeping the complexity low with these languages. Alan Kay also had a really interesting. He's been working on an operating system that I think they made a complete operating system with like a Office like document editing suite and everything in I think 50,000 lines of code or something like that.
Wow.
And the sort of I will link to that video as well in the description, but he has a bunch of presentations about this, and they also made like a domain specific language for drawing graphics, etc. And the core idea was that, like, if you design language that, just like you said, like it only contains the salient parts of the problem, then you can create a compiler or a runtime that takes care of the how, like exactly how is this supposed to be executed. Then the user can focus on the what, like, but the what is always different, right? Like it matters if you're designing, if you're writing like a PlayStation game, or if you are writing like, a banking backend or something like that. They have completely different things that they care about. So just like you said, it needs to be domain specific.
Yes. It's fascinating, all these projects, and yet Smalltalk is forgotten. Alan Kay's favorite language, right? And Prolog is forgotten. Prolog was a fantastic achievement at some point, completely forgotten by now. I feel that it's not an end of history for programming languages as such. It's we're just now realizing that it must and it can be made easy for users to make their own languages. And how to do that. So there are principles behind that. Functional programming gives you principles that if you adhere to those principles, you don't go wrong. Your programs will not crash. Your semantics will be easy. It will be easy to understand what your program is doing. There won't be x equals x plus 1 anywhere. And
no more
that kind of thing. Yeah. So that kind of thing is a set of principles. Is not just, I was talking at the beginning of our conversation about features for programmers who write code, but there are also a set of features for designers of programming languages. So programming languages must be designed with these features. And if you do that, there are very few features, but if you do that, you have unlimited power, and you can dial down that power if you want to. You can dial it up if you want to. You can put more features or fewer features. There's a system F, for example, and there's system F omega. And if you delete certain things from system F omega, then you get system F. Still a very powerful system. But in that system, you cannot do monads. And you cannot do monad transformers. For example, you cannot do free monads. You can do specific monads only. And that's okay, maybe, for your users. But your users will never be able to define, for instance, a function that works with any monad.
Yeah.
No, because it doesn't...
some kind of higher order, you need kinds for that.
Right. So it's called higher kinded types. The name, I don't think it's very good, but that's what it's called. So it means that you have a type parameter, which is itself a type constructor with another type parameter. That's what it means. So monad is a difficult thing to understand, partially because of this. And because it's a kind of an arbitrary type constructor with properties. It's a difficult thing to grasp without a lot of examples. So you have to start really with a lot of examples, and then you can get to that idea. So you can dial down the power if you want to, or you can dial it all the way up to dependent types. The principles remain the same, the guarantees remain the same. All the dependently typed languages like Agda and Idris, they're total. They're guaranteed termination, exactly the same story. So you can dial all the way down to like system F, and you can even do less than system F. You can say, oh, I don't even want type parameters. I just want our specific types.
So like Go version 1.
Exactly, Go version 1. You can go all the way down to that power if you believe that this is good for the users, and and yet all the guarantees will remain in place. Your implementation wouldn't even change so much, and it will, you'll just comment out certain parts of it, and so on. And so this is a set of principles that help you build new programming languages with guarantees, with mathematical background that ensures that everything will be working fine, with no strange features that will be buggy for reasons unknown, and so on. I mean, you can have bugs in your implementation, but if you don't, then
so what if you would summarize, what would these principles be?
Strict typing, functions as first-class values.
Oh, yeah, it's like the ones we talked about in the beginning.
Right. You can have, if you want, you can have records and union types. You don't have to, because with functions you can encode them. You can just mimic them if you have first-class functions. That's it. You can add features as needed. Type constructors, more difficult, more complicated type constructors with type parameters and blah, 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 blah. Dependent as you can add, you don't have to, but you must have strict types, immutable values, first-class functions. If you have that, you are done. You will never have any trouble at the fundamental level, like trouble with Java, C++, where the program compiles and then it crashes at runtime. For no clear reason. You don't know why. Somewhere you believe something is not quite right, but you can't point your finger. Can't put your finger on that. Because the type system of C++ and Java is not sound. You can write programs that type check, where all the types seem to be correct, but the types aren't actually correct.
It's unsound.
Unsound. It's impossible to check. It's impossible to find that error. So
you don't want that.
No. Yeah. But that's what everybody is working with, and people don't realize the loss of productivity that they have had, and yet this is a Turing tar pit. So they accept that things will be buggy. They accept that errors will be hard to find. It's just accepted because we have, we invested so much into these languages, and these languages do deliver us the value that we want, So we don't want to go and think,
Yeah,
it's like I have a
the devil you know.
Yeah, I have a blunt tool, but it does the job. I mean, I'm sweating working with it, but that's life, right? I couldn't possibly spend any time sharpening my tools. I have no time, I have to work.
Yeah, and then I guess there's also a certain pride you get after a while, after having mastered this, like, difficult and like kind of unpredictable thing that you like. Now that there's, I guess there's a bit of a sunk cost fallacy as well. Like, I spent so much time learning this. Like,
Right.
Now you're telling me it wasn't necessary or something like that. But
right.
Yes, it's been great talking to you, Sergei. I think we have to start wrapping up now. But before we end, I would like to ask you if the listeners now, like, you've got them all worked up, excited to start writing their own programming languages. Do you have any recommendations for where to start? Like, how do you learn to write your own programming language?
There are quite a lot of tutorials about how to implement Lisp. I would actually suggest to do that. Lisp is much easier to implement than most programming languages. It doesn't have types. It's very simple in syntax. And yet it's just as powerful as all. It was the first functional programming language, and it's just as powerful as all they are, but less easy to use, of course. However, implementing Lisp is relatively easy. There are lots of books and tutorials about that, how to write your own Lisp, your own scheme, or something like that. So scheme is a kind of a modern version of Lisp, more modern. Or there's something called Racket.
Oh yeah, Racket
it's a language,
really cool.
Language workbench where you make your own languages using Racket. Well, I don't know if that's a great idea. Maybe I would rather say I would use my own favorite programming language that I know very well, right? Like for me it is Scala, for other people it could be anything else, it could be C++ or Java or whatever, using the language that you know so that there is no friction, but you learn how to implement this weird thing, this functional language, which has very few constructions, and somehow implementing these constructions must be done just right, and then you have a lot of power in.
Then you have a Lisp.
Yes. So first, if you understand how to implement Lisp, then you can go on to look at type checking and all those other things. Implementing Dhall was for me that experience. I did not implement Lisp. I implemented Dhall. But I already learned quite a lot about programming languages by that time, so it was possible for me to understand the documentation. But I would say, Lisp is the good first step, and there are lots of materials about this. Lots of people. It's like Monad tutorial. Once you understand how to implement Lisp, you want to write a tutorial about it because it's so good. It's so easy. Yeah.
Yeah, it's kind of like a revelation. It's like, it's like, it's not that much code either. It's sort of like, I remember when I wrote my first implementation, I was like, oh, is that it? Like, then you realize that, like, okay, it's like just like the core of the Lambda calculus, it's like extremely simple. But
yes.
Like,
and yet you do everything.
Yes,
and
much
and
more
yet you
powerful.
can do everything now. You can do MapReduce. You can do monads if you wanted to.
yeah.
Right.
Yeah.
Okay.
And then I guess for like learning about type systems and stuff, there's always the Types and Programming Languages book. Have you read that?
Yes. Unfortunately, I cannot say what is a good book about learning types and how to do typed languages. There are lots of books. I'm not sure how good they are from the point of view of learning. Unfortunately, there is a lack in the literature. There are academic books that tell you about theory of types and all those things, and mathematical properties of languages and all that. And there are books that tell you how to, implement a small C compiler on assembly language. And there's very little in between. So if you are just starting to learn, I'm not sure. I mean, I would say actually, Gabriella's GitHub with documentation about how to implement Dhall is the best book you could have at the moment.
Okay.
If you already understand this notation, which is just syntax for Prolog, really.
The Gentzen notation.
Exactly. This is the big gamma, and then turnstile and all this crazy thing. But this is essentially the syntax for Prolog. I see it like that. But once you understand that syntax, you can translate that into your favorite programming language pretty easily. And Gabriella's site has all that. And the entire language is laid out with full detail. Nothing is left out. So you can go step by step understanding how that works and implement Dhall, or part of it, not necessarily entire language, and see how the simplest typed programming language works with very, very limited amount of features. Type checking is very, very limited. There is like one place where type checking is done, and there's no type inference. There is no fancy stuff like Haskell's, type classes or magical stuff like that. No, syntax is very straightforward. Even parsing is very straightforward for this language, and so that is, in my view, it's not a book, but it's essentially
a good starting point.
It will be
maybe that's what your third book should be about.
I would only write a book if I have something to say. I don't want to just repeat what somebody else has done. Maybe I will include a small appendix into my book implementing a very small language, showing how that is done. Unfortunately, I don't yet know the right techniques. I'm still learning.
Okay.
So there are quite new, interesting techniques for implementing languages. People are talking about them, and Gabriella certainly used them, and I haven't yet learned. So I don't write books, repeating what somebody else said without fully understanding it even. I don't want to do that. It's a lot of material I don't yet understand. I need to get through it first.
Yeah, but if anyone listening knows a lot about type theory and wants to write a book, there is a hole in the market that's screaming to be filled.
Yes.
Okay, but yes, I think we'll have to wrap up now. But thank you so much, Sergei, for coming on the podcast, and thanks for sharing all of these interesting details. And links to the books and everything will be in the show notes.
Thank you.
And yes, thank you. Yeah, and we'll see the listeners, or we'll be back. Let's put it like that.